Hello, my name is Jeremy Comel and welcome to part 4 of the LipidMatch tutorial series. In part 4 we're going to be discussing how to interpret your LipidMatch outputs after you successfully run LipidMatch. Now, if we looked at our RStudio script, we'll see this note: there are 50 or more warnings after it has completed running the script. So that's how we know that it's finished running. And this is completely fine. Now, we can look at the folder which we used as an input, and we'll see a new folder generated called output. We double click this folder. These two files, neg-ID'd and pos-ID'd, or just one if you only have one polarity, are the most important files for LipidMatch. If you double click this, you'll see why. You get your feature list just as you had imported it. And then along with that feature list, now you get the lipid annotations. 1_ represents that it's identified by data dependent. Let's scroll through. And if you look at 3_ represents that it's identified by data dependent, but only by class. So it only saw the class-specific fragments, but no fatty acyl-specific fragments required for identification. Now, we can also look to our right. There's an intensity ranked. So this shows the sum of all the fragments, their intensities. So you can see here where we have ceramide D18(1)/17:0 is our internal standard. And here's the fragment intensity showing that it's the most likely and dominant peak within that feature table. You can look at other examples. So for example, PC16:0:18:1. You also get co-eluting 16:1:18:0 and 14:0:20:1. You can see here that it does rank the lipids as you'd expect based on their relative abundances in biological samples. And here you can see the actual ranked intensities to see how much, get a general idea of how much of each composes of that feature. In addition, we've tested this against MS-diol and Greasy and found that the top-ranked lipid matches in most cases, and so it's been confirmed and corroborated by other software, this ranking algorithm. On the right, you can see the lipid class for the top-ranked lipid, as well as the adduct, and whether that feature was only identified as one lipid class. So for example, if we scroll down here, you can see that there was a plasmanyl and plasminyl lipid identified for the same feature. So it says no, there wasn't the same lipid class identified. Now, we can also take a look at the positive mode just to get an idea. Here again, you see the feature table, and we scroll to our right. Here's our cholesterol esters. And you can see here, if we scroll all the way down, that you get this 3_ sometimes without a 1_, which means it was only identified by lipid class, not by the fatty acyl constituents, based on the fragments observed. So you might get numerous identifications in that way. Now, if we scroll all the way to the end, you can also see 4_. This means that it was identified only by exact mass. Usually, I'd throw out all data below this point with 4_ or more, because these annotations are highly tentative. Now, if we continue scrolling down, you also see features where there is no exact mass hits and no MSMS identifications. We also have tables like neg-only IDs, which show all the identifications before they are aligned to features, in case you wanted to look at all of them. Finally, what we have, which is an important and unique aspect of LipidMatch, is you can query and look through all of the information that LipidMatch used to identify a feature. So if we double-click this data dependent folder, we get 4 subfolders, each one confirmed either by class or by fatty acyl constituents in a negative or positive mode. So let's look at negative polarity conformation of phosphatidylcholine. Here we can look, and if you read the first column, it says what the criteria the user used to identify the fragments. In this case, the fragments had to be above 1,000 intensity and had to be greater than or equal to 1 scan for each of those fragments. So if we look at PC 12:0, 16:0, you can see that we saw the neutral loss of the methyl and the formate, and we saw the 2 fatty acyl chains. Another lipid that would be more common, for example 16:0, let's say 18:1, you'd expect many more fragments. Indeed, you see almost all the fragments. What I like to do is you can go to View, and you can freeze the panes. So now you can see all those fragments. So let's look at our 16:0, 18:1. We see almost all the fragments that are possible. The retention time min and max shows the retention time for that lipid feature where they were looking for those scans. Then you can also see the retention time where each fragment was most intense. Which scan at which retention time was that fragment most intense? You can see it's 8.24 for most of these cases. Now you can see the number of scans. So in this case, for PC 16:01, 18:1, all of the scans confirmed. All of the scans were confirmed in at least 2 scans in this case, or 2 scans. In some cases, maybe only 1 scan did you observe the fragment. Again, you can check for each of these new roles. You can look at, there's titles that will describe what those columns represent. Now, if we move through, we also see the maximum intensity of each of those fragments. So we can look and we can say, oh look, this ion 12:0, 16:0, this is sheet plasma, is very low in abundance in its fragmentation. But if we were to look at 16:0, 18:1, you can see that these ion intensities are much more abundant. In addition, you can see that, for example, the acyl chains as negative RCOO minus ions are the most abundant, which is what is expected. So you can check these ion intensities to make sure they match what you'd expect, since LipidMatch doesn't do that for conformations. Now you can also look at the average experimental mass to charge, as well as the theoretical mass to charge. So you get a lot of information on each lipid and its fragmentation. You can also check, using the additional files, if certain lipids weren't identified. So let's say we wanted to look at the bile acids, and we looked at all confirmed. In this case, it shows some potential bile acids that were matched based on exact mass. But as you can tell, there was no fragments confirmed for any of those fragments for any of those species. Let's take another look. Let's say cardiome lipid M-2H. In this case, you can see that certain fragments were observed. So you can scroll through this, and you can see certain ones that might be more potential to have existed, even though you didn't see all the fragments needed for confirmation. Finally, one file that's important to look at is the parameters. So let's say we're looking at our PC as the formate addict, and we wanted to see what are the parameters we used. So some parameters we can we can read things. Some of the parameters are universal, others are not. So it shows you when the computation started and ended for PC. So you can see that it took about 9 seconds, or yeah, I think this is less than 9 seconds, so probably 9 milliseconds to run this library. And then you can also see the directory of the MS2 file that was used for this one, the feature table that was used, as well as the library that was used. You see your confirmation criteria, so in this case both the fragment in column 10 and 11 had to be confirmed, which were those negative fatty acyl chains we discussed earlier. The mass to charge window, retention time window, minimum scans, and minimum intensity, which are going to be the same for all libraries. So that concludes the interpretation of LipidMatch outputs, and I look forward to seeing you in future LipidMatch tutorials.